So welcome everybody. Good morning. Thanks for coming, and thanks to our speaker Venkat, accepted our invitation to give a talk in our distinguished Warren lecture series. So I know Venkat for a long period of time. I first met him in AGU when I was doing a postdoc with my advisor at Georgia Tech and Rafael Brass. It's a connected community. And so since then, Venkat has played role in my mentorship during my assistant professorship time, and we have stayed connected. And thank you for coming to our department. I don't know why I'm biased, but I always think that University of Minnesota is the most beautiful university on the planet.
Little biased.
But in any case, Venkat, I just learned that, well, he did his bachelor degree in Roorkee, India, and then came to the United States, a master's degree in the University of Iowa, and then moved to Princeton and did his PhD in Princeton with Eric Woods. And then he worked for Goddard Space Flight Center for 3 years as a postdoc and research scientist, then moved to the University of South Carolina. And then now he has been in University of Virginia for 6 to 7 years. And now he holds a chair, a professorship at that university, the Department of Civil and Environmental Engineering. Venkat, his resume is long, so I need to look. So Venkat has supervised 25 graduate students, has more than 200 publications. He's currently serving as chief editor of Vegetation and remote sensing in Earth System Science journals. He has served on the National Academy panel for the Decadal Survey of Earth Observation from Space, as the chair of planning committee for groundwater recharge and flow. He's currently serving as a member of the Water Science and Technology Board, National Academy of Sciences, and vice chair of Earth Science Advisory Committee for NASA. And he's the next president of hydrology section at AGU. Can't wait to hear about your story, and the floor is yours.
Thank you so much. Thank you so much, Albert. Thank you. Thank you very much. You know, I came to University of Iowa in 1987 to study hydraulics and hydrology with Vitek Krajewski, whose probably best friend and collaborator was your own Effie Fafula Giorgio. And so I heard a lot about Minnesota. And at that time, I knew there were 3 great places for hydraulics in the country: SAFL, IHR, and Colorado State. Now, obviously, hydraulics has taken, different turns. There is still problems in hydraulics, but SAFL and these other 2 great places still remain relevant. My last visit and only visit to Minnesota was January 31, 1989. Vitek, me, and Jim Kramer came to take the software and learn the software called a company called Ultimap. This was predecessor to ArcGIS. This is a cold January day. We came in Vitek's Saab. It's a very good car, very nice car, Saab 900S or something. But at lunchtime, all these people in Ultimap were going and starting the car. And I'm thinking, what are they doing? And then come evening, Vitek's car door was frozen. The car door opened, and then the steering column was frozen. So Jim and I had to push him a few times around the parking lot. And then I got into the back seat, and 5 hours later, I woke up in Iowa City. So when Ardashir said, "Can you come for a distinguished seminar?" I said, "Absolutely." He said, "Maybe in the spring." I said, "No." Now, Ardashir is biased. He is biased. He works on cold regions. Now I realize why he likes Minnesota. But it's a great place to be, and I'm so thankful for that invitation. And so my talk today is study of hydrological extremes of space. Please free to stop me. And in my enthusiasm, I may have loaded in a bit more slides than I can go through. So please stop me at any time. So, the motivation of this talk is, understanding hydrology is no longer scientific. It's a huge societal impact. And for that matter, there are so many programs in NSF as well as at NASA which talk about Earth impact or, applications. So science is very important. Absolutely. Want to do fundamental science, but applications are actually equally important, and they can lead to fundamental discoveries. And what are the impacts of climate change? Long days have gone in measuring just CO2 on top of Mauna Loa. We are looking at other impacts in the water cycle. I call hydrological extremes as floods, droughts, landslides, permafrost thaw, and wildfires. And my intent is to give some examples of each of them here today. And the questions, the last two are the questions which obviously is not going to be answered in this talk or anytime soon. It's like, what is the two-way feedback between extremes and the hydrological cycle? You know, what happens with climate and anthropogenic activities, and how do they alter the landscape? I know some of the big work over here has been done in sediment morphodynamics at in this department and at SAFL. So outline is motivation, some tools, and again, the tools is just for me to brag of what we did recently, and then these things, and then some examples of droughts, floods, landslides, permafrost, and wildfires, then an integration, and then final. So almost about 10 years ago, maybe 8 years ago, I started and served on this National Academy's decadal survey. And the question for hydrology, because there were 5 panels, and one of them was hydrology and water resources, is water and energy coupling, you know, acceleration of the water cycle, rain, snow, evapotranspiration, and extremes. Prediction of changes, you know, how does land use, land cover change, and water use modify the energy cycles? What are the short and long-term consequences? And the 3 is availability of water coupling with biogeochemical cycles. And the 4 is hazards, extremes, sea level, etc. Now, this is a published report. I think it's 520 pages long, but the water and hydrology part is only 100 pages. And I'd urge people who are interested in looking at questions to read it, because the relevance of it is that it deals with basic hydrology problems. Of course, the added incentive in that report is how can NASA design sensors and missions in order to study these processes and variables. So it's still basic hydrology. So people sometimes mistake NASA as, oh yeah, it's not that. I mean, it's a very concise, and for one, it will provide a lot of literature for people who want to read it. And it's available freely on the web. So this particular report had 5 questions over here, or 5 big areas, and big questions. And these were solid earth, water, weather, climate, health, and ecosystems. And these big areas all have connections to water. That's the best part. I mean, I could not have imagined when I was a graduate student at Iowa, first at Iowa, that I would work with MDs understanding the link between environmental variability and public health. I would have never imagined. I mean, I thought I was as far away from medicine as I could be. And so now you can see public health, and I'm just wrapping up this 10-page preliminary proposal for the ERC due on Monday, 40 people. And a big part of it is public health, because when people breathe the wildfires, they get particulate matter, and PM 2.5 and PM 10 are very important. So actually the quality of life is a big emphasis on many NSF large grants. And so the connection between wildfire, which is caused by a drought or a flash drought, and public hydrology and public health now becomes exceedingly close. So there are a lot of things. So early warning, floods, landslide, permafrost. I pretty much could have put everything there, but I just put the top ones on the right-hand side. Ecosystem services, you know, the landscape provides a lot of value to environmental health. And so, you know, you can see over here. Now we are in a very golden age of remote sensing, golden age. Everything started in the 1980s. I mean, everybody has heard about Landsat. Now it's even easier. If you go to Google Earth Engine, you can apparently download Landsat data on the fly. You don't even have to download the data sets. You can do everything over there. That's what I'm told. I don't use the computer too much in that sense. But Landsat and vegetation is one of the most important parts, because land use change impacts hydrology and water the most. Very, very important. And then, of course, it's followed on by numerous NASA sensors, the AVHRR, Advanced Very High Resolution Radiometer, and then MODIS, Moderate Imaging Spectroradiometer, doing vegetation index and surface temperature, followed by wetness and rainfall. With rainfall, the big ones, and I know Ardeshir here has done a lot of work with rainfall, is Tropical Rainfall Measuring Mission, and GPM, which is Global Precipitation Mission, which is probably nearing its end in the next decade. And then we have soil moisture. We have a lot of stuff with soil moisture, and we'll show you those things. And water level, one of the recently launched missions, now it's not recent anymore, almost nearing 2 years now, is SWOT, Surface Water and Ocean Topography Mission. And then you obviously have the atmosphere. So if you put this all into a nice cartoon, then this is how it looks. You know, you have the water cycle, you have different sensors. Some of them are still working, some of them are phased out. Most of the times, the stuff you get from these sensors are indirect observations. They're not direct. So you still have to use some amount of physical, mechanistic equations to convert, let's say, observations from MODIS into evapotranspiration. It's still a good measure, but it's not a direct observation. The only direct observation is when you take your thermometer and put it in the water and say the water temperature is 30 degrees. That's the only direct observation. Even in that, I can say, oh, what if the temperature, the thermometer is not carefully calibrated? So these are all indirect observations. So a lot goes in between that bird in the sky to the data sets you get on your computer. And so those are the parts where, you know, all our inputs can help them make better. And then ultimately, we are bound with these two big equations in hydrology. One is the energy balance, which is net radiation plus sensible heat plus latent heat plus ground heat flux is 0. And the other one is the simple water balance. Precipitation minus evaporation minus transpiration minus surface runoff is the change in the water storage of the layers. So these are very important, and this is what we use. So if you put this all into a nice cartoon, a movie, you can see very easily. And again, this is all four different measures. It's not the same sensor. It's not even on the same satellite or the same orbit. The vegetation index becomes greener when the precipitation goes up and down the intertropical convergence zone, especially in the continent of Africa. That actually increases or decreases the liquid water thickness, the amount of water in the column. And you can see the surface soil moisture also varies with the rainfall and looking at reflected through the vegetation content. So this is reasonably a good way to see it. And obviously, a movie like this will not solve any science questions. You have to take it and slice it and dice it to see the actual time and space scales and variabilities. So if you look at hydrological extremes, you have floods, you have droughts, you have landslides, you have permafrost thaw, and you have wildfires. And all of these are very, very important because, you know, almost every day we see something related to weather and climate, which involves water or the hydrological cycle. And this is just 2022. It's from NCEI, if I'm not mistaken, and it is cartoon off the web. It tells you how many disasters occurred, and they're all on the billion-dollar scale. So, you know, the exact numbers are not written here, but we have another slide probably for it. And right now, you know, Helene is causing billions. I mean, I don't think it's billion anymore. It's billions of orders of magnitude of disaster. And then if you look at this since 1980, this is the cost. And again, these are all from public websites, so it's not something I did research on. But you can see droughts are a lot, but wildfires are catching up. You can see there were a few fires burning in Southern California even a few days ago. And then there is flooding and landslides and permafrost thaw. So trying to motivate this by using climate change, one of the things which is very important is precipitation. Precipitation is the most important part of climate change. Let's face it, because probably the largest component of the hydrological cycle is precipitation. If you don't have rainfall, you don't have hydrology. So I always joke with my students in the fluid mechanics class I'm teaching in the fall, when it's raining outside. I said, rain is not a 4-letter word, but it's job security for me because I'm a hydrologist. So if you don't have rain, it's no point. And that is my joke. It's not from Letterman, sir. So we have done some research on rainfall. We are not atmospheric scientists in our group. You know, we are more, hydrologists. So this was just published in GRL earlier this year. So it's very simple metric. The number of days it takes to fill 50% of the bucket. That's it. Just very simple. It's changed from 1950 to 1985 to 1986 to 2021. Number of days to fill the bucket. That's it. So it's like just like telling you, oh, you give you a buffet on Monday morning and you can't eat the rest of the week. But the buffet will have all the food items from Monday through the next Monday, as opposed to spreading the food out. So this is the problem. So it's not spreading out. Ideally, they used to tell, where I lived in South Carolina, it should rain every other day. Farmers, they know this stuff better than all of us. They have the rule of thumb. Every other day it should rain in summer. And so Helene is pushing all that rain, which would rain every other day, in a matter of 24 hours, which is too much. It's an overdose. You can't, the land can't absorb it. So same here. If you look at this, and you look at this cartoon of, this is only for Europe, and we're trying to expand this for the globe, as you will see in the next slide, is that if you look at this, you see that most of the places, the number of days that the difference, the later period and the earlier period is much a few days. And this shows that the climate is trending towards more bigger storms. So in a shorter time period, you're filling the bucket 50%. And the similar thing we have been doing, and this is not published, so please don't publish this before my students. Job security. So you can see some places, and this is more difficult because look over here, the time periods are shorter. So you can't talk of climate in 10 years. It's a little tough to pass that argument. So we are being very careful on what to say in this, but we are doing something else, which actually makes a lot of sense. So with soil moisture, it's one of the most important variables because it determines how much water infiltrates and how much water runs off. One of the problems in the state of Georgia right now was it was raining before Helene and the rainfall reached it. So it was already soaked up. So there's no more capacity for the water to go in. Not that it would matter because it was so much of rainfall anyway, but the initial wetness is very, very important. It determines the memory, land surface memory. When you have slow soaking rains, land surface memory determines how much water infiltrates and how much runs off. But most soil moisture estimates, I mean, you hear about rain gauges and stream gauges. You can even hear about groundwater monitoring wells, but you don't hear about soil moisture sites. Maybe some farmers have it in their fields, but most of the time soil moisture has been only measured or observed in USDA experimental watersheds or in experimental facilities. So what happened, it's about 20 years ago, NASA and ESA started planning these big missions. One is SMAP, soil moisture active passive, and one is SMOS, soil moisture and ocean salinity. And they have been providing really good data sets trying to characterize soil moisture, as I'll show you. Now, relating soil moisture to the extremes, wet soils on steep slope promote landslides. Permafrost thaw increases infiltration, reducing overland flow. Dry soils and low vegetation content are precursors of wildfires. And this last one is very important because all of you will remember what happened last August in Maui in the Lahaina fire. It's all that short grass called guinea grass which caught fire. The tall trees were actually unharmed. So this has a very, very big environmental implication. So the way to improve or obtain higher resolution soil moisture, we have 1 kilometer and 400 meter resolution soil moisture is by using this invert relationship between soil moisture and day-night temperature difference. If the day-night surface temperature difference of the ocean surface is about 2 degrees, you can go to the ocean at 2 a.m. and at 2 p.m. and the difference will be 2 degrees, maybe 4 degrees. And that's at this end of the spectrum, high soil moisture. Obviously, ocean is all water. And then if you go to the desert, you'll see the day-night temperature difference is huge. I mean, if you went camping, if some of you have camped, then you can realize that it's a huge difference and it's a very, very low soil moisture. And that's the concept of thermal inertia. So using that concept and using a whole bunch of publicly available models and data sets, we make these lookup curves to see and downscale the soil moisture. And obviously, one of the things we do is validation. All of these 1 kilometer soil moisture is validated with 1,600 sites all over the world. So it's not something we just give out saying that, believe me, this is good. So if you can look over here, the 1 kilometers and the 9 kilometers show you on a global scale, it's much more difficult to see because 1 and 9 appears the same. But if you start going down to smaller scale, like this one, it's of Sacramento, San Jose River Basin and the Danube River Basin, you can see starkly the difference between 1 and 9. The 1 kilometer gives you a little bit more pixelated results. The reason with the edges are abrupt is because of the downscaling system. So no attempt has been made to smooth out anything. So you can use a filter and smooth it out, but we are not doing any smoothing. We're just giving you the data sets, and you can see that they are much a higher resolution. And this one is 9, 1, and 400 meters, and you can start seeing the beauty of the pixelation. Now, some of this is also because the gaps is because of clouds, because for the downscaling, we use temperature, and surface temperature is not seen when you have clouds in the way. And if you go to an even smaller river basin, the San Pedro watershed, you can start seeing the real fun stuff. When you look at processes like biogeochemistry of small catchments, soil moisture is an important component of it. And using a 400-meter resolution soil moisture is much more apt for these studies than using a 9-kilometer or even a 1-kilometer soil moisture. So the high resolution soil moisture is very important for it. And this is all available free of cost at this NSIDC data set. The 1 kilometer is available. Actually, this has increased till 2024. So we have it all almost current availability. The 400 meter is still being, the data set is ready, but the paper has not been accepted. So we'll upload the data as soon as the paper is accepted. So one of the other toys which we bought and started using is this L-band radiometer. It's on a UAV right there down below, and it has an L-band radiometer. It's a pretty expensive thing. I joke to people, it's one of the few things I have which is more expensive than my car. It's pretty big stuff. So if you look at this, and so this is a pretty nifty thing. It's launched by an air gun, and it has obviously a battery, and it flies pretty fast. I can't remember the exact speed. And then it lands. The only problem is it's in landing. It doesn't have landing gear. It does a belly landing. It does a belly landing. So it rattles around. So it is important to land on soft grass or soft soil. Of course, it has had a lot of breakdowns because of the landing, and some things get damaged. But this is the first one of its kind. It built in Boulder, Colorado. And so we published a paper out of this. We run this in the USDA watershed facility outside Washington in Beltsville, Maryland. We're helped by Mike Kosh and Andy Russ, who actually even keep this instrument out there. And you can see the wetting and the drying patterns, and we can fly it whenever we want. We just launch it, fly it, get the data. So the advantage is it has great resolution. I believe this is a 5-meter resolution of soil moisture. So if you want to see something on a very high scale, this is the way to go. So going into each of these things, and a short blurb. It's my talk is more like a dim sum. It has a lot of stuff. So you can, take whatever you want selectively. So floods are one of the hydrological extremes, and this one was in Lake Victoria Basin, written by G.G. Power, who since graduated. And you can see that this river basin suffers actually floods and droughts, and we use all of the data sets come from publicly available data available on the web. And what you see in this, which is very interesting, is you can go from a lot of rainfall, for example, October 2019, to very little rainfall just 2 years later in November 2021. And that's the interesting thing. So it's not like it's a long, drawn-out drought and it 10 years in the coming. The reaction time is very quick. And, it's not just for us, but it's for the people who do the relief. They have to know this stuff. And you can see how this looks like. But the story in this is more about the soil moisture. So if you look at this, and this is just one example for this time period, the 2020 and the 2021, the one part which is wet and the one part which is dry, you can start seeing sub-pixel heterogeneity in this dry part. And even though most of the part over here seems to be all dry in the 9 kilometer, in the 1 kilometer, it just still shows little heterogeneity, sparse of wetness. And this is at a 1 kilometer scale. So why is this important? This is important because when land use planners or people who do insurance or plan crops, you have to know where you should plant what. And this one figure is not going to give you all the results. And I'm by no means trying to say that. But if you take this over 10 or 20 years and plan a histogram and look at the probability of that particular pixel being, very dry or very wet, that'll give you an idea. I mean, most people in the insurance industry do this, but they do it for houses. They'll say, if you're too close to the river, forget it, we're not going to insure you, because they don't want to pay out a premium every time the river level rises. But in this case, this is more for bigger regional planning. The government says, okay, you can't locate farms here because it's not going to be useful. Just because it's wet a few years doesn't mean you do it, because one year it may just blow up and the whole thing may be flooded, and that's not good. So now the opposite of it is droughts. And we have worked a lot in South America, and this is the La Plata River Basin, one of the largest river basins in the world. And, as a matter of fact, we've been working with the US Department of State, Army Corps, and NASA conducting, training courses for them. And it's actually the site of one of the largest hydroelectric dams called the Itaipu Dam. It's really big. I've never been to a hydroelectric dam, though I'm a civil engineer and my father was a civil engineer, but this is really amazing. And this one is also another problem. So Brazil has had a drought in the past few years. And the droughts, again, when you look at droughts, you can always do modeling or you can always do observations on the ground. But the way we do it is we're using global models or global observations. And this gives you a bigger picture of it. And this is all continental scale. So, you're looking at the whole continent rather than just one river basin, trying to see how it sits with the perspective. And this is using groundwater percentile from GRACE and surface soil moisture percentiles from, I think this is from the model, coupled with GRACE, obviously. And what we did was we tried to see, hey, if we use our 1 kilometer soil moisture, can we track this drought? And so you look at the soil moisture, you can start seeing, if you look at the month of August, it starts getting drier and drier before it wets up. And so that's very, very important for us to see. And, it has really given us a lot of information in this regard. And then coming closer to home, we have been involved for a couple of years now on flash droughts. One of the biggest flash droughts was in the summer of 2012 in the Mississippi River Basin. I don't know how many of you remember it, but it was a huge drought. And flash droughts are worse because they come about in a matter of weeks, not in months or years like I showed before. And so we have been working with the Army Research Office funded projects trying to figure out how to relate flash droughts to hydrology and how to detect it beforehand using remote sensing, which is very important. Now, the third part, changing gears a little bit, is a really, really difficult one. It's difficult because it is a really small scale. When you think about landslide, you don't think 9 kilometers or even 1 kilometer or even 400 meters. You're talking about 10 meter, 20 meter landslides are very, very small. And so trying to figure out how this happens is a very complicated matter. And there's a lot of models, one of them being at NASA Goddard, and my former student Chelsea wrote this. The first thing with this landslide is trying to construct an inventory of landslides. And this has been done by the good people at NASA Goddard. So, you have all these landslides inventory. So what we tried to do is we tried to do a frequency ratio analysis to see where is the landslide the most. So we classified the land use classes from the original to a new classification, and we tried to use a very simple frequency ratio metric. And the frequency ratio metric is very important because it will tell you if you take agriculture and leave it fallow, that's the worst to do. Because when you were doing agriculture, yes, you were disturbing the land, but at the very least, as a farmer or the owner of the land, you were making sure the thing didn't flow away. You know, you had protective systems. So even though people say, oh yeah, forest is wonderful to prevent landslides because it's original, you're not disturbed it, it's actually not true. If you change agriculture and walk away from it, the chances are that place will become victims of landslides. And that's what, you know, so we saw that agriculture to forest has the highest frequency ratio. So we have done a lot of this. But on the other hand, the most important thing for it is precipitation. The triggering mechanism for any landslides is increasing pore pressures brought about by precipitation. You increase the load on the slope. And so we have had lots of studies to figure out what kinds of precipitation results in landslides events, what's the triggering mechanism, and this has been very useful and also published. Now coming to what Ardeshir enjoys the most, or permafrost. So a big project concluded in high mountain Asia, where part of the landscape is dominated by permafrost. Now, mapping permafrost is the most difficult thing to do because these are inaccessible areas, and you're not going to go there to get observations because it takes a long time to get there. And some of these areas are so far away that getting there is probably impossible unless, you know, you have some kind of magical transport. So what we did, we tried to use the readily available land surface temperature from MODIS. And again, this is like a few thousand kilometers across and a few thousand north-south. So, and then try to map the land surface temperature and then correct the land surface temperature for snow cover to map the permafrost. So when you look at permafrost, when the mean annual ground temperature, or MAGT, is greater than 0, you could have permafrost, but it's not much. If you start going up the curve and to the left, you increase the chances of permafrost. And these are all established. So our improvement in previous metrics, and there are previous metrics on this, and the person whose name is out there, Gruber, was the one who published a lot of literature on this in the past. What our interesting is trying to use this and try to do the zonation, not using climatic variability, but using actual variability. Because you can have a region, permafrost, and go away from it and then come back into it. So instead of using, you know, a static product, we are using a dynamic variability. And this is how we wrote it. And we compared it with what Gruber had. Some places match, some places do not, but, you know, it's a good. Now, this one is very interesting. And again, no pictures. It's almost accepted. So this is, we wanted to move from Himalayas to some place closer to home. So this is the Andes, and we are trying to look at the depleting snow cover and changes in stream flow. Because many of these catchments, the only source of water is snowmelt. It's not, they don't get rainfall. It's like a paper we just finished and published on Afghanistan. Afghanistan gets no rainfall. It just gets snowfall. And so all the farmers do is wait for the snowmelt. And if the snow fails that year, what they do is start drilling and pumping out groundwater. So there's only two sources, groundwater and snowmelt. And you really don't want to use groundwater because it's, as I call it, a savings account. You know, you don't want to touch your savings. You don't want to touch your nest egg. So that's the problem. The problem also in this area, and if you look at these figures, and the snow cover has been decreasing, and also the temperatures have been increasing, as shown in those pictures. And in the next slide over here, the temperature trend, you can see these are, we were just talking this morning about ERA5, you know, ERA5 temperature trends. And, you know, it's pretty horrifying to see. And again, most of our studies deal with larger scale scales so that you can see the bigger picture. Trying to figure out just exactly what happens in one small corner is much more complicated. Coming to wildfires, which is the topic of my ERC, hopefully goes out and comes back successful on Monday. The state of California has been a big victim to wildfires, and nothing has been affected more than the upper Feather River watershed. And the three biggest wildfires, probably in this century, not the three biggest, but the top 10, are in the state of California. And the Camp Fire, the North Complex Fire, and the Dixie Fire are mentioned here. And these are all large areas. I mean, can you imagine the response needed in these isolated rural areas to put them off? This is really, really a complicated item. We are going to talk just about this one North Complex Fire. This is how it looks before, after, true color images from Landsat. You can really see it. I mean, it's not that difficult to see. Green, August 9th, brown, August 12th. And what we also see is hydrological variability. See, our whole thing is to map this on large scales. We don't really want to go into minor stuff. This was just published in JSTARS earlier this year. So you can see the soil moisture. Interestingly, what happens after a fire is the surface of the soil gets coated in a hydrophobic layer. And the vegetation dies, as you can see. Vegetation dies in the middle panel. So no more soil moisture extraction from the bottom. So as a result, the soil moisture goes up. And you can see the ET goes down because there's no vegetation to do evapotranspiration. And this feeds very nicely into my next slide, which has just been submitted, no pictures. So a storm in 2006 and a storm in 2017 look similar in rainfall, but where you see the hydrographs are completely different. And this is all simulations by HEC HMS. Very, very similar when you had the native vegetation and when you had the same storm after the fire. So hydrology gets changed a lot, not to mention sediment pollution, sediment, soil erosion, etc. And the reason for this, most of the reasons of this is that the parameters, when you are using something like a HEC HMS, you have to calibrate it, and the calibration, the parameters are completely different, between the two sets of simulations. And also is different is the peak discharge, the percentage runoff, and all kinds of metrics related to soil moisture and vegetation index and the simulated discharge. Both the base flow and the direct runoff changes. Even though the base flow seems reasonably similar between the two storms, before fire and after fire, the direct runoff is a huge, huge difference because of the altered surface conditions. So now trying to wind down a little bit here. We all talk about importance of remote sensing, and nothing captures it better than this paper by Hung a couple of years ago. And this is in Journal of Hydrology. So we did a very simple experiment, so simple that an undergraduate could do it. They're smart too, I'm saying. I'm not trying to pass judgment here. So a very small river basin over there in Vietnam called XL, Shala River Basin. We took an off-the-shelf hydrologic model, off-the-shelf, SWOT, Soil Water Assessment Tool, calibrated it for 10 years, and then ran it for 10 years using rain gauges. Very simple. This really, anybody can do this. And you get calibration, you get Nash-Sutcliffe efficiency of 0.8, percentage bias, and then for validation, you get that, because you have to freeze the parameters. Then we use GPM. This is a very small watershed. It's really, really small. But we use GPM, precipitation, right off the shelf, no calibration. And we calibrated the model, and then we ran the model. It's amazingly different in the second 10 years. Whereas the model running with the rainfall data from the rain gauges, a small catchment had 3 rain gauges. And you do kriging to fill in the rainfall for the SWOT model. It gives you a p-bias of 25%, but worse still, the worst part is it's missing all those peaks. I mean, the peaks are where the damage and destruction and the importance of hydrological extremes lie in. But this is able to capture all the peaks. And the answer is very simple. I mean, obviously, anything you get, you want to explain. Whereas kriging interpolates data between the rain gauges through some Thyssian polygons or whatever method you want to use, the satellite may be wrong. It may be completely wrong, and I'm not going to defend it. But the spatial variability of it is good. So the inaccuracies in the actual amount of precipitation gets fixed in these parameters. You know, what are you calibrating your model for? You're calibrating so that you can get rid of incorrect observations and incorrect physics. That's the only thing you do. So you can get rid of biases in calibration, but you cannot get rid of these spatial variability problems.
Did you plot the variance map during the training?
Yes.
What was the variance?
The variance map of the rainfall, yes, we have it, but I'm sorry, I don't have it right here. But I can share it with you. Yes, it's a huge difference. It's two different things. It's two different things. Yeah, you're completely right. And then we can plot it for the big storms, or we can plot it for an average for the whole 20 years. Yes, absolutely. And so it's a huge difference. That's the difference. The difference is spatial variability. So remote sensing is not going to solve everything for everybody, but it can solve you things where you need variability. And most of us do need spatial variability, unless you're working in a very, very small area. Now, I spoke about a large area, and then we have this eco-stress, and this is standardized crop stress from eco-stress related to crop productivity. I believe this is in Chile, work of my student, Benjamin Goffin. And you know, I think it's in review, or it's going to be published, or whatever, one of the two. But you can see that eco-stress is a sensor on the space station. And you know, now you're talking about really, really small stuff, you know, 400 meters pixels for these large systems. And Chile depends a lot on agriculture, especially growing grapes, because they are one of their largest exports is grapes and wine. So how do we bring all of this together? This was a paper I wrote, 2018. This is the one I was talking about. And if you look at 4 different variables of the hydrological cycle: precipitation, runoff, evapotranspiration, and water equivalent thickness, or groundwater, if you want to call it. If you look at the Mekong River Basin, you can see that January 2005 was very dry, and September 2011 was very wet. This is rainfall anomalies from the TRIM data set. And that translates into runoff. And that translates into ET, evapotranspiration. And with a lag, that translates into the water thickness. Now, the beauty on this is not that we discover something new, obviously not. But it's all 4 different things. The precipitation is from TRIM. The runoff is from a model. The ET is a derived product from a sensor. And Gray's water equivalent thickness anomaly is a completely different sensor. So using different items from different sensors, we can piece together the story of the hydrological puzzle. That's very important. And the same thing we show in the Murray-Darling River Basin for it to, for wet and dry periods, and the same reflects. And obviously, the Grace has a much poorer spatial resolution, and that is seen from these spatial plots. Now, the whole point is to compare. So I'm sure many of you know the Amazon River Basin, and many of you know the Murray-Darling River Basin. Amazon River Basin, beautiful, green trees, lots of water, lots of camping and hiking if you do that. And then Murray-Darling River Basin, mostly managed agriculture, small towns, farms, and highly urbanized agriculture. So if you calculate a very simple index called monthly rainfall anomaly divided by monthly climatology, this is how the Amazon looks like. So the month-to-month variability, I'm not talking about year-to-year, month-to-month variability of rainfall is very little in a climate sense, very little. And guess what muddy darling looks like? And this is the same scale. This is dimensionless, so you can compare it to each other. So I always joke with people that that one is the heartbeat of Usain Bolt after he runs 100 meters. Right? Easy. He even looked back in one of those races. Imagine if he hadn't. And that is my heartbeat. I can run 100 too. Not as fast, but I can pin power. But that will be my heartbeat. So the thing is, the rainfall, precipitation, is the heartbeat of an ecosystem. And you cannot control that. I mean, that is, again, you can predict it due to changes due to climate and all that stuff. And absolutely. But in the end of the day, the ecology, the ecosystem, land-atmosphere interactions is governed by that basic fundamental variable of precipitation. And nobody can run away from that. So I want to end where I started my career at Goddard. Robert Goddard was the inventor of the rocket. And he said, it's difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow. I don't think I want to belabor anything on these thoughts, but I want to leave you with the hope of tomorrow from last AGU. So these are the people who are going to do the stuff and wow you guys. So fund by NASA, and thank you.
Thank you so much. We have time for a few questions if you might have any questions.
So I have a question, because it seems that you have projects all around the world,
Yeah.
and you manage to provide answers with satellite data.
Yes.
But then you're developing this very high resolution drone for 5-meter measurement.
Yeah.
What is the?
That's very good. So, I mean, the last mission of NASA, which was conducted, called SMAP, was $800 million. The mission with NASA and ISRO, NASA in US and ISRO in India, called NISAR, is about $1 billion. Sooner or later, the politicians in these countries are not going to sign those checks. So what I call these UAVs are remote sensing on demand. So you have Hurricane Helen going over. Obviously, during a hurricane, you can't fly a drone. There's no way to do that. But after the hurricane, you can fly a drone to survey the area very quickly. Local areas. I'm not talking about flying it all over the state of Georgia. So to me, UAVs are remote sensing on demand. So they're somewhere between a Radio Shack toy, the kids using those things to photograph, to an airplane. So airplane can do too. If you have a fitted airplane with these sensors, it can go pretty fast. I mean, you can crisscross America if you want with it. So I think this is the future. And it is being developed in some way. So some of these satellites, like Planet, sensors like Planet, they're not in one box. They're, toaster, bread toaster sized boxes, just, called CubeSats, circling all over the sky. So I think the future is going to be in distributed remote sensing. Not that remote sensing is not distributed, but in smaller units. So to me, trying to understand the problems of the landscape, it depends on the problem you have at hand. But I think UAVs are probably the easiest, because you can just press a button, pull it out of your garage, and launch it and use it.
Okay, so you need there is a need for that resolution.
Yeah.
Okay. Thank you.
Thank you so much for showing all these different examples where the tools are there to be used to address some sort of hazards. And because these examples do have a lot of impacts for human lives and economy and so forth, like I was wondering if you have any experience that you can share about how you're able to get these results in the hands of managers who make decisions on the ground, and how that might influence what they do.
I'm very happy you asked this question, because I don't think we have to do that anymore. In the past, I had to be a salesman, but unfortunately now, I don't think long ago, one of my mentors told me that, Venkat, you can sell a used car in Baghdad. So, I was so convincing to him. But you know, the people in the insurance industry are clamoring to get these data. You don't have to sell it to them. And of course, all of this is publicly available data. So the one person from, to be unnamed, does wildfire risk for a big reinsurance company. They wanted this 1 kilometer data set because they want to have an index called risk. Now, how they do it, I don't know, but they just want these maps. So the people in the businesses of economics and healthcare, they want to come and take it. It's not like I have to sell it to them. And besides, this is all public stuff anyway. Yes. Yeah. Yes, but I do not know what they do with it downstream, but they have in the past come and taken it from. And again, with more wildfires, there will be more people getting that thing, for example. And insurance companies are one of the biggest. They're really worried about some of these disasters. I mean, guess what? All the data published after Helene is going to inform these insurance companies, and they're going to, there will be some shifts in the market. And that's, it's our job to make sure we publish the best results and data sets, because they're not going to read our paper in Journal of Hydrology, but they will look at the data sets and say, oh, this has been a repeat offender with flooding. So we don't want to insure we don't want to give them, we don't want to point out Ardhashear's house and say, don't insure it, because that's not what we should do. They can figure that out, but we can provide the inundation depths or inundation frequencies so as to inform economic decisions.
Thank you. Any other questions? I need to be here. Any other question? All right. So thank you so much, Venkat.
Thank you so
We
much.
appreciate you taking question. Thank you.